So in the last video, we got into some pretty crazy examples. I mean, if you look at what's written on this page, that's pretty intense and overwhelming. If you stepped into this class for the first day today and looked up at the chalkboard and saw this all written up there, you'd probably be like, yeah, this class is not for me. But hopefully when we went through it, it made some sense. None of the individual steps are that hard. The challenge is just keeping straight what you're doing on each of the different lines. I think there's a good analogy to life right here. You have this huge, overwhelming task that you start out with, but as long as you break it down into different steps and you're really careful about keeping your work super organized and clear what you need to do, each of the individual steps aren't all that bad. Anyways, we did those 3 examples in the last video, but I had 2 more examples I wanted to work through. So that's what I'm going to do in this video. In this first problem, what we're asked is to figure out the derivative of x cubed times e to the x times the log of x, a product of 3 things. We haven't seen how to take the product of 3 things yet. Like, is there some super product rule? I wrote power rule here, but I meant product rule that applies when you have a product of 3 things instead of 2 things. Well, actually, it turns out there is, but I haven't taught it to you yet. So if you didn't know that rule at all, how could you attack a problem like this? Well, common theme in this class, if your problem is not written in a way that's conducive to the rules that you currently have, maybe you can rewrite the problem. This is something times something times something. There's something called the associative property that says when you're multiplying together 3 things, you can multiply together any 2 of them, take that answer, and then multiply that answer by the 3rd thing. The product of x cubed e to the x and log of x is x cubed e to the x times the log of x. Think about it like, I don't know, 2 times 3 times 5. If you're multiplying 2 times 3 times 5, what you can do is multiply the 2 and the 3 first to get 6, and then multiply the answer by 5. That gives you 30, the same answer you'd get if you took the 2 and multiplied it by the product of the 3 and the 5. The 2 times the 15 would also give you that same 30. Anyways, the idea I'm trying to get across is just we can rewrite this problem this way. And when you rewrite it this way, maybe it's a little bit easier to see the rules that you're going to use. Because the way this is written is it's something, that something happens to be this expression in parentheses, times something else, the log of x. So I can use the product rule. What I would do is I take the derivative of that first something, x cubed e to the x in this case, and then I'd multiply it by the second something, the log of x. To that I would have to add the derivative of the second something, the derivative of the log of x, and then multiply that answer by x cubed e to the x. If you look down here, you're kind of looking for your d over dx symbols. Over here, you're like, yeah, I could take that derivative. Over here, you're like, that derivative is going to be a little bit harder. I'm going to have to use the product rule there because it's something times something. So what I would have to do is take the derivative of the first thing, the derivative of x cubed, and then multiply that by the second thing, the e to the x, and then add to that the derivative of the second thing, the derivative of e to the x, multiplied by the first thing, the x cubed. Be really careful using the product here, created 2 different terms. I'm supposed to take the answer to that product rule and multiply it by the log of x. I better make sure that both of those terms, the entire answer to this derivative, gets multiplied by the log of x. The first term that resulted from the product rule up here can be rewritten as you see down here. To that I'm going to add the derivative of the log of x. You might wonder why I'm not taking that derivative in this step. Hopefully it'll become more clear in the next step. And then I got to multiply that by x cubed e to the x. I've broken things down sufficiently where now all that's left are 3 different derivatives. The derivative of x cubed, no problem. I can just use the power rule. The derivative of e to the x, that's the best derivative out there. It's just equal to e to the x. And the derivative of log of x, remember when there's no base written, the 10 is implied. So this is almost 1 over x. We just have to remember to multiply that x by the natural log of 10. I got 3 derivatives left to take, and all 3 of them are very manageable. I should just take those derivatives and be done with this example, right? Right? No, I'm not going to. The reason why is because I want to illustrate something for you. I could take this log of x and distribute it through these parentheses. Why would you do such things? Don't worry about why. Do you at least believe that you could? You have something plus something times log of x. You can distribute that log of x through to get rid of these parentheses. If you did that, you'd have the derivative of x cubed times e to the x times the log of x. That's getting the log of x and multiplying it by this first term inside the parentheses. When I multiply it by the second term inside the parentheses, I would have the derivative of e to the x times x cubed times the log of x. Distributing this log of x through the parentheses produces what you see up here. I still have this last term, the derivative of the log of x, times x cubed times e to the x power. You're like, okay, I mean, I guess you could do that, although I don't see why you would. It almost feels like you're simplifying this thing right here before you do the calculus. Typically, you've been doing the calculus first and then simplifying your answer. Why are you doing things different? Because look what we produced right here. What we produced right here is something that's really powerful. I know it might just look like a big jumble of symbols, but remember the original question was the product of three things that we were trying to take the derivative of. And what we ended up with here are three different terms. And the first term, we take the derivative of the x cubed, and then we leave the e to the x and the log of x completely alone. Kind of like the product rule, but not exactly the product rule because we have three things being multiplied together, not just two. In our second term, we take the derivative of the e to the x, leaving the other two things alone, the x cubed log of x. And then in our third term, we take the derivative of that log of x, leaving the first two things, x cubed and e to the x, completely alone. What I'm saying is it turns out that there's this kind of super product rule. I don't think anybody uses that term except for me. And what it says is if you're taking the derivative of a product of three things, what you do is you take the derivative of the first thing, leaving the next two alone, and then you take the derivative of the second thing, leaving the first and the third alone, and then you take the derivative of the third thing, leaving the first and the second completely alone. If you encountered this problem in the future, you wouldn't even need to go through the step of adding the extra parentheses and then using the product rule once and then using the product rule again. What you could do is just kind of use this super product rule to immediately jump over to here, which I think will make your life a lot easier. And it's worth pointing out that this super product rule, again, trademark Brian Stone-like, I guess, doesn't just work when you have three things. It works if you have 4 or 5 or 6. If I'm multiplying together 10 things here, take the derivative of the first, leave the other 9 alone. Add to that the derivative of the second, leaving the other 9 alone. Add to that the derivative of the third, leaving the other 9 alone. You'd end up with 10 different terms in there. It's kind of cool how that works out. Anyways, I guess we should finish the problem, although really I've kind of blown the punchline already. The derivative of x cubed is 3x squared. I got 3x squared times e to the x log of x from this first term. For my second term, the derivative of e to the x is just e to the x. So I got e to the x times x cubed times log of x for my second term. In this third term, the derivative of log of x is almost 1 over x. It's 1 over x times the natural log of 10. So I got 1 over x times the natural log of 10 times x cubed e to the x in my third term. No d over dx is left. Therefore, I'm done with the calculus. Therefore, if I want to be, I'm done with the problem right here. Probably won't surprise you to hear that I will choose to take this a little bit further. What I'm going to do is think about this x cubed e to the x is up in the numerator here. And then I'm going to cancel this x with one of these x's. So really it's x squared e to the x up in the numerator here. And then I'm going to look at this and be like, wait a minute, I got e to the x in all three terms. And in fact, I also have an x squared in all three terms. So I'm going to factor out an x squared e to the x from all three terms. What that'll leave me with in the first term is 3 times the log of x. In the second term, if I've pulled out the e to the x and an x squared, I'm left with just a single x here. So I would have x log of x. And in the third term, I'm factoring out x squared e to the x, so the e to the x is gone, x squared is gone. I know it looks like x cubed, but remember we're canceling one of the x's with this x, so it's really just an x squared. That gets pulled out in front, so this entire thing is gone, and I'm left with just 1 over the natural log of 10, this x being gone also because it canceled with this x. You certainly don't need to, but it's cool if you can recognize that these answers are equivalent. So the first idea I wanted to get across in this video is there's this, I don't know, superpower rule, and it ends up being kind of nice. You don't see it a whole lot because how often are you taking the derivative of a product of three things? But when it does show up, it sure cuts out a lot of work for you. The second point that I want to make is completely different. The second point is, it turns out you can take the derivative of the derivative. And it's not just something you might do for fun. I know the word fun might be kind of strange to use in this context. It turns out that it has some applications that are really useful. If we think about the derivative as the rate of change, the derivative of the derivative is the rate of change of the rate of change. And it might surprise you to hear that that has a very practical meaning in a lot of different word problems. For example, if your function models position, we've already talked about how the derivative would give you velocity. The change in your position is your velocity. But what is the change in your velocity? Well, it turns out that if your velocity is changing, you're accelerating or decelerating. So the second derivative, in that instance where the function gives you position, ends up giving you acceleration. You don't need to worry about any of those applications of derivatives for now. Right now, we're just focused on taking derivatives. Later on in the class, we'll talk about using the answers we came up with. For now, I just want you to see that somebody could ask you to figure out the derivative of the derivative. And they wouldn't say figure out the derivative of the derivative. They'd say figure out the second derivative. And while they might say the second derivative, nobody would write the second derivative. You'd instead use this notation, which makes a lot of sense, right? The little prime meant the derivative, so the fact that there's 2 primes here now kind of implies it's the second derivative. Suppose we have this function, we want to find the second derivative. Well, the second derivative is the derivative of the derivative, so it makes a lot of sense to first figure out the derivative. What's f prime of x? f prime of x is the derivative of x squared e to the x. Wait a minute, this is something times something. I better use the product rule. It's the derivative of x squared, the first thing, times e to the x, the second thing, plus the derivative of the second thing, e to the x, times the first thing, x squared. Compared to some of the examples we've done in the last few problems, it's fairly straightforward. You might not even need to show this step. The derivative of x squared is 2 times x, so I get 2x e to the x is my first term, and then the derivative of e to the x is just e to the x, so I get x squared e to the x over here. Perfectly acceptable answer the way it's written. However, I want to make the point that if you wanted to, you could factor out x e to the x from each of these terms, and what that would leave you with is a 2 over here and an x over here, because the e to the x is gone and one of the x's in x squared is gone, but we still have the other x. The first derivative can be written this way or it can be written this way. And up to now, it really doesn't matter. I mean, pick whichever one you want. But now, for the first time, we're using our answer to the first derivative to go a step further. We want to calculate the second derivative. And when you're calculating multiple derivatives, by the way, you don't need to stop at the second derivative. There's such a thing as the third and fourth and fifth derivative, although we're not going to do them in this example. When you're calculating multiple derivatives like that, you really want to spend some time taking a look at your answers and thinking about which one you would rather take the derivative of. In this specific case, I don't know how much it matters. I think it's about the same work either way. And I'm going to demonstrate it both ways. But often one answer is significantly easier to take another derivative of, and it's definitely worth your time to stare at those and think about the steps ahead of time. So if I'm taking the derivative over here, I have a sum, something plus something. That's great for derivatives. All I'd have to do is take the derivative of this thing and the derivative of this thing. So before I write anything at all, I'm thinking in my head, can I take the derivative of this? Can I take the derivative of this? Because if so, I'm good. Yeah, I can absolutely take the derivative of this, but it's going to involve the product rule, right? It's something times something. Can I take the derivative of this? Yeah, but it's also going to involve the product rule. It's something times something. So I could take the derivative of each of these two terms individually. Each one will involve a product rule, but it'll be a fairly easy product rule. In fact, this second term right here is something I've already taken the derivative of. I already know what the answer to the derivative of this is. It's this entire thing. So taking the derivative of what's written right here won't be too bad. What about over here? Well, if you're taking the derivative of what you have over here, you might recognize that you have a product of three things. X times e to the x times 2 plus x. So maybe you'd use your super product rule over here. You don't have to. I mean, you could think about it as a product rule problem, this stuff times this stuff. And when you're using the product rule, you'll have to take the derivative of this side. And when you take the derivative of this side, you're going to have a product rule again. So you could think about this as a product rule inside of a product rule, although I think it'll make your life a lot easier to use the super product rule over here and take the derivative. And I think if you use the super product rule over here, you'll find it a little bit easier than the work over here. Anyways, without further ado, let's take the derivative of this thing. It's something plus something. Don't forget the rules that you learned in previous videos. This is something plus something, and the first of those two somethings have a coefficient, the number 2. So I could say that the second derivative of x is 2 times the derivative of x e to the x plus the derivative of x squared e to the x. What's the derivative of x e to the x? Well, we got to use the product rule. It's the derivative of the first thing, the x, times the second thing, the e to the x, plus the derivative of the second thing, the e to the x, times the first thing, the x. Be a little bit careful. When you use the product rule in here, it creates two terms. If you write things the way they're left right now, the 2 only gets multiplied by the first term. You get an incorrect answer. I got to make sure that I have these parentheses right here so that the 2 hits this entire thing. Otherwise, my derivative's not going to be correct. What about over here? Well, I guess you'd use the product rule, and you'd say we have the derivative of x squared times e to the x plus the derivative of e to the x times x squared. And if that felt really familiar, maybe you'd be like, wait a minute, I don't even need to do that. This was the original question. I know what the answer is going to end up being. This entire thing is going to simplify to exactly what I have in this box right here. Is it reasonable for a student to make that connection? I don't know. I bet some would and some won't. Maybe I'll continue the problem assuming that you didn't see that connection, and I'll just do all the work. We have the derivative symbol written, 4 times? So I guess we've changed this one problem into 4 different problems. The good news is none of those problems are hard. The derivative of x is just equal to 1. So I got 1 times e to the x, in other words, e to the x. The derivative of e to the x is just e to the x. So I have x times e to the x. Again, careful with the parentheses. Over here, the derivative of x squared is 2x. So I got 2x e to the x. And then over here, the derivative of e to the x is just e to the x. So I got x squared e to the x. Could you leave your answer like this? Absolutely. You could be done and call this good. However, it's worth pointing out that you could simplify things. There's a more direct route to do it, but I think what most students would do is first get rid of these parentheses by distributing the 2 to get 2e to the x plus 2x e to the x plus 2x e to the x plus x squared e to the x. And then maybe they'd be like, wait a minute, 2x e to the x, 2x e to the x, that's the same thing. So I don't just have 2 of these x e to the x things. I got 4, 2 here and 2 more of these x e to the x things. So I got 2 e to the x plus 4x e to the x plus x squared e to the x. This is a great answer. I'd be thrilled if you got this far. However, it's not the only way you could leave your final answer. You could also recognize that each of the 3 terms has an e to the x in them. So you could factor out that e to the x and get 2 plus 4x plus x squared. I'm kind of partial to this final form right here. I think it looks kind of cool. But any of these last 4 lines would be totally appropriate and great answers. Difficulty level of this is a problem. I mean, it's the entire problem really, but just figuring out the derivative of what's underlined in blue here. I don't know, maybe like a 5 or a 6. I mean, it's hard, it's not impossible. You got to be really careful showing your work. I bet a lot of students would forget parentheses here and wouldn't have a 2x e to the x here and would end up getting the answer marked incorrect in like a homework system or something, even though their answer was really, really close to correct. So yeah, there's lots of little possibilities to make mistakes. But once you get the hang of the product rule, it's not horrible. But the point that I want to make is it certainly involves some difficulty, right? It's not easy by any means. Let's compare that difficulty with the difficulty that we'd get if we took the derivative of this expression. We're still figuring out the same thing, the second derivative of x, because remember, either of these are equivalent expressions representing the first derivative. So what we want to do now is take the derivative of this thing. But again, if you recognize the super product rule, I think I called it the superpower rule earlier, but I guess that makes no sense. Hope I didn't write that. I did. Wow, that makes no sense at all. Sorry, this should be super product rule here. Superpower kind of sounds better, like it sounds like a superhero, but we're not using the power rule, we're using the product rule twice. So I guess this name makes more sense. Anyways, when we're taking the derivative of a product of 3 things, all we got to do is take the derivative of the first one, the x, and then leave alone the e to the x and the 2 plus x. To that we want to add the derivative of the second thing, in this case e to the x, and leave the first and the third things completely alone, x times 2 plus x. And then finally, we want to take the derivative of 2 plus x and then leave the first and the second things completely alone. The derivative of what we have written in purple here is what's written on this line. And the great thing about this line is I think we're just one step away from getting our answer. The derivative of x is just equal to 1. So I got 1 times e to the x times 2 plus x. The derivative of e to the x is just e to the x. So I got e to the x times 2 plus x. And then the derivative of 2 plus x. You could write this in multiple steps, but I bet you're at the point in the class where you can just look at this and tell that it's the derivative of 2 plus the derivative of x. And the derivative of 2, because it's a constant, is 0. And the derivative of x, my variable, is equal to 1. What I'm saying is the derivative of 2 plus x is just equal to 1. So I get 1 times x times e to the x. This is a great answer. You could leave it just like this. We don't have any derivative symbols left, so we're done with all the calculus. However, you might recognize that you have an e to the x in all 3 terms. So if I pull out that e to the x, I got 2 plus x times 2 plus x plus x. Can I clean up those parentheses a little bit? Yeah, absolutely I can. I got 2 plus x plus, instead of x times 2 plus x, I can distribute the x through and get 2x plus x squared, and then I still have this last x out here. If I combine like terms, for my constants I have a 2. For my x's I got 1x, 2 more x's, and 1 more x, so a total of 4 x's. And then for my x squareds, I just have the 1x squared. What you see is what I end up with on this line is identical to what I had up on this line, arguably a little bit easier if you're comfortable using this super product rule.